Okay, well, looks like we have a few people coming in, but we'll get started anyway. Hi, everyone. I'm Ryan Blue. I am a member of technical staff at Databricks. I joined a year ago through the Tabular acquisition, where I have been working on open data formats and more specifically Apache Iceberg.
And my name is Dan Weeks. I'm also an employee at Databricks, and I am also working on Apache Iceberg. I was one of the original creators with Ryan back at Netflix, where we designed and built it originally, and been working on storage, table formats, and catalogs for a long time now.
And actually, what we're talking about today is very exciting because it is basically the unification plan for Iceberg and Delta that we've been putting together over the last year or so. So hopefully you are into, very deep in data formats because we're going to go there. But first, everyone please read this statement about forward-looking statements. We of course, are not making promises. I never make promises. So, yeah, read carefully, please. All right. Also, just want to say, please complete the surveys through the app. This helps us put together a better program for the next time. We really appreciate you guys taking the time to do it. All right. And with that, we can get started. We're talking about the future of open table formats. So this is basically the work that we're doing at Databricks with both Delta and Iceberg community members to unify the table formats. And we just want to present and talk about where we're headed today. Now, there are actually quite a few pieces of this that we'll cover. So first of all, we're going to talk about what unification is, what it means, and our strategy for unifying the formats. And of course, anytime we're talking about unification, keep in mind, much like the forward-looking statements, that we are contributors and we're participants in the open source communities. So while we as Databricks might have opinions or preferences on how things go, we don't claim to control those communities or be able to even make promises. So yeah, I don't make promises. We're also going to cover V3 and sort of what that contributes to data level unification, and then go into a strategy for the rest. So looking at both Delta and Iceberg table formats, the opportunities for unification, and then sort of the strategy that we're putting together for how that could take place. Of course, I also always want to mention that I don't want you guys, well, I mean, maybe the people in this room, this seems like a small enough group, but I don't want many people actually caring or thinking about data formats in general. In the course of your day as a data engineer or a data analyst, maybe building ML models, you should generally just have a platform that works without needing to think about it, without being surprised by random behavior of like zombie data when you rename columns and things like that. So please don't care about table formats. That's not the point. But there is a big component here that you do need to care about, which is architecture. So what is the format that you choose? What is the effect of that on the architecture that you want? I think that most people here are pretty sold on the lakehouse architecture, and that's really what we're trying to unlock, right? The foundation and bottom layer of a lakehouse architecture is open data formats that allow you to use your central copy of data that is well governed through a central catalog with basically any compute that you need in order to do your job. So hopefully you care more about architecture than formats. But we are going to talk pretty much about formats today. Now, you might be thinking, well, why? And I think it's a good topic to just go through and talk about how we are going to do this. But if you are someone who just cares about architecture and capabilities and things like that, I would really encourage you to go to Brito's talk later today. So Jonathan Brito, he's giving a talk on, essentially this phase 2 here in the middle. This week, I think today, our announcements are that we have used Unity Catalog to effectively unify table formats. If you come in through Unity APIs, everything looks like Delta. If you come in through Iceberg APIs, everything looks like Iceberg. And we try to make that as seamless as possible. If that is the thing that you are primarily interested in, I encourage you, go check out Brito's talk as well. But right now, we're going to skip ahead to phase 3, to the very end, and talk about what we're doing to unify the table formats, hopefully in the next couple of years. Okay, so you've been warned. We're going to go. And I will, for unification and our approach, hand it off to Dan.
Thank you. So I'm going to go ahead and start from a very high-level view of why are we even talking about this? What motivated this? How did we get to where we are today? And a lot of that really has to do with distributed processing, how it evolved over time. It's been 20-ish years since we had like the MapReduce papers and HDFS, and that's really the origins of a lot of this, even cloud-based distributed processing. But at the time, it was an engineering challenge, not an analytic challenge, not a SQL challenge. It was how do we process, sort, do all of these challenges with large amounts of data and cheap commodity hardware. But then over time, what happened is we had the introduction of the cloud. Cloud brought object stores, infinite storage, a bunch of different capabilities that really didn't mesh well with those original technologies that we built for data processing. And that's because they were built off of things like file system constructs. And over time, as we started to rely on the processing mechanisms and looking for guarantees from the data, it's not so much about like how big is it, it's how correct is it? Are we getting the results that we're expecting? Do we have the guarantees about how it's changing and evolving over time? Do we have the constructs that we need for data engineering, data analytics, data science? We saw that there were major gaps. And this is where the community, in many different areas, started exploring, ways to address this through cloud-native or cloud-first solutions. We did this at Netflix with the introduction of Apache Iceberg. Databricks was addressing similar challenges with the introduction of Delta Lake. Different communities were looking at these problems from different perspectives. And it's only natural that people find those problems, they're addressing their localized challenges, and they're fixing things either in correctness or performance or something related to this dramatic shift that we had in the infrastructure. So multiple technologies evolved over that period of time. And where we ended up is that we actually now, there are many projects that have disappeared, they're exploratory, but now they, like Iceberg and Delta, have emerged as incredibly successful projects. And just to give you an idea, there are exabytes and exabytes of data that are stored in these two formats. Both of them provide many of the same capabilities now because as they started in different locations, they started closing gaps in terms of the behaviors, the guarantees that they provide. Asset operations was one of the very first things that everybody was interested in because of the kind of object store guarantees, eventual consistency. These were kind of the first things were addressed, but then you move up the stack and you start solving things like schema evolution and its performance and a bunch of other features around these table formats. But that caused a rift in terms of, as time goes on, you've got huge amounts of data in both, and then there's a question of, what is the kind of matrix of things that I need to do to solve my problem? Which one is the right one? Does this solve this problem better? Now I've got both of them. So this has become a problem for the industry as a whole, where you have similar capabilities across two different representations, and now you have to make a choice. And what we want to do is we want to alleviate that choice. So this is why we talk about unification. So what does unification look like? Well, we want to address this working with both communities in a way that advances the state for everyone. We don't want to be making negative trade-offs in one place or another in order to achieve unification. And one of the best things about this is we've got many different open source communities that are tackling the same challenges, We work very closely together. The Parquet community, Avro, Arrow, Delta, Iceberg, these are all related technologies, and we're all solving similar problems. So we've been working together, but we also want to make sure that we're learning from each other's mistakes and taking the best of everything to move forward. We also want to make sure that we're making strategic investments so that we can make the smallest amount of change and get the most amount of value out of it. Really niche features, really niche capabilities. Like, we do want to address those over time, but we really want to get to the value first. So when we think about this in terms of unification, we've kind of deconstructed the table, or this, the storage area, into three main areas. One is the data layer. Ryan's going to talk a lot about V3, but this was a major focus of what we were doing in V3, making sure that that data that you're going to write and you're going to keep for 10 years looks the same, can be interpreted the same, has the same types. And that's really critical, because that's the most painful part of any sort of migration or anything, is like, hey, go rewrite that petabyte of data because we changed something. Let's not do that. The next one is what we're calling kind of the content metadata layer, which is how do we represent the constructs of the actual underlying table representation, what's active, what's old, how do you time travel. These kind of things are all part of the metadata content. And then at the top level, we've talked a little bit about Unity Catalog. You have the catalog layer, which has a bunch of behaviors and capabilities that are built around the table formats themselves. And so there's these distinct areas that we're focusing on in terms of what does it mean to actually unify formats. There's also ecosystems. There's lots of libraries that interact with Iceberg data. There are lots of libraries that interact with Delta data, tools, capabilities that these different libraries bring, integrations with engines. And what we're saying here is that these things are part of the surrounding ecosystem, and they each provide kind of unique value. So what we don't want to do is remove that value. What we do want to do is have a common representation, so that when somebody reads that data, manipulates it in some way, and then produces a new set of data, that the next tool, despite what ecosystem or language or capabilities it has, can interact with that data in the same way. So it's really getting to a common representation. With that, I'll hand it to Ryan, and he'll go through V3.
All right. Yeah, so we're going to hop into data unification, which is that lowest level, essentially Parquet files that persists for so long. We wanted to get a start on that. So there are not too many differences here. Not surprisingly, you store an int32 in Parquet underneath Delta, the same way you store an int32 in Parquet underneath Iceberg. But there were differences, and we were actually starting to diverge in some key areas. So what we first did was we looked at, what are the types that are in Iceberg but not Delta, or Delta but not Iceberg, and where do we need to get our hands around this problem? And what we're going over here is the Iceberg side of the problem. There are some gaps elsewhere that we're going to cover at the end, like time type, but those are actually harder problems because Spark itself doesn't support time type right now. So although Iceberg does, you haven't been able to use it in Spark for a long time. But on the Iceberg side, we found that we could introduce some really valuable changes that get us a lot closer to unification. So we're going to go through those. One of the marquee features of Delta Lake is deletion vectors. Now, Iceberg also supported a row-level delete format, but we encoded, from the Iceberg side, we encoded the deleted rows as file reference and position within that file, rather than having a DV per file and then a position within the DV that's deleted. Now, this was just a incompatibility for a long time, but we also had other issues with Iceberg v2. So v2 in Iceberg introduced the row-level delete format, and it actually was too permissive. So we thought, you might want to be able to encode another file of deletes and then send that off and then asynchronously compact that later. And it turns out that when you allow people to do things asynchronously, sometimes people just never do them at all. So we had tables that had thousands of delete files against data files, and essentially people complaining. And when people complain about table formats, we have a big problem. because people should not be thinking about these things. So what we did was we introduced synchronous maintenance and better tracking for DVs. So we made the design a lot more similar to Delta, and we actually incorporated the same DV representation so that the DV files that Delta uses are compatible with Iceberg and vice versa. So this is basically making our representation of row-level deletes across the formats nearly identical, which is a great step forward for anyone trying to use deletes. What's actually going to happen in a month or two is we're going to, again, I'm not making any promises, no forward-looking statements here. But in a month or two, we're going to release the ability to take your Delta tables and use them with the Iceberg interface using a V3 structure for those delete files. So it gives us tangible benefits right away. I should also say that this was a great example of collaboration across communities. We got Delta people involved in the Iceberg mailing list talking about, yes, it is important to have synchronous maintenance. Here's what we learned from the Delta side, and it was a really great example of the communities coming together. As was row lineage. So row lineage is a lesser known feature within Delta called row tracking, where you get synthetic row IDs for basically every single row in the data set. And you also have a label that tells you what version of the table a row was last changed in. So that's actually really important for really high quality change data feeds. So if you want to know exactly what changed, even through like a copy on write operation, you can either go and compare every field of every row to figure out, what rows were just caught up in this copy on write operation and unchanged, but were moved to a different file, or you can actually use this metadata to target the rows and get really fine-grained changes. So another great thing that we're adding to Iceberg that is important across all formats. Next, I want to highlight a couple new data types. So variant data type is probably the biggest one, where for the longest time, people just kept putting JSON into their columns. And despite those of us on the side of you should always have a schema, people just kept doing it. And then when I caught myself doing it, we all do it. Actually, this is a really great story where we, as Databricks, brought to the the Spark community, a new variant type and variant format. Essentially, let's attack this problem and be able to store a binary representation that you can access super quickly and have some heuristics for pulling out data as top-level Parquet columns so that you can actually get the Parquet benefits. So we did that. Then actually the Iceberg community and Snowflake in particular picked up that work and said, hey, we should use this everywhere. And so we said, yeah, that sounds like a great idea. And we all decided to move the specification into Parquet so that every Parquet file and downstream derivative of Parquet has this ability as well. So we're delivering this in V3. It's also in Spark 4.0, coming in, I think, Delta 4.0 as well. So it was a really good story and a fantastic feature for those of you who just have semi-structured data and don't want to use JSON parsers all the time. Lastly, we've added geospatial types. And like the other things here, this was a collaboration and really represents something new that was not part of unification. But if we added it separately, then it would have made the unification problem harder. So we decided to pull it into Iceberg v3. Again, standardize the types in the upstream Parquet community, work with the Delta and Iceberg communities to get those specs updated. And now we have geospatial data types coming. So now you don't have, if you have map data, you don't have to just use Hive or some binary representation. You can actually have a data lake architecture, lakehouse architecture for geospatial data. So we're really, really excited about that. And of course, there are more things. So we're standardizing default values, write defaults, initial defaults across both formats. We're working on additional type widening use cases and things like that. And we're also delivering these on the Delta side through Iceberg Compat v3 features that should allow you to take advantage of these as you access your tables as Iceberg tables, even though they are, they were originally Delta metadata. All right, and with that, we're gonna go and talk a little bit more about the metadata layer. Oh, am I? Okay, mic's back on. That's the quick update on the data layer. So a lot of good progress there. The next layer is metadata. So how do we take the content metadata, or this tree of metadata files that we use, and figure out how to move to a common representation that is a benefit to both communities? In order to do that, we want to talk about the state of both projects right now. So for Iceberg, I'll hand it back to Dan.
Thank you. And what we're going to do is we're going to take a kind of quick visual peek through what is this Iceberg metadata that we're talking about, so people can kind of have a general understanding of what it looks like today, and that's going to be really helpful in the next section. So when we talk about Iceberg metadata, we often refer to it as a tree structure, and everything is navigable from one central point at the very top of this tree, and that tree actually encompasses both like historical versions of the table, but most of what we're going to be focusing on is what we call the content metadata. So this is the metadata and how it points to files in the actual object store. Now, these are files as well, but the way that we construct the tree currently in versions like 1 through 3 is that we have this two-level structure of metadata. The top level is the manifest list, and the manifest list is pointing to a series of manifests. In that manifest list, you have information about the manifests, like which partitions they pertain to, statistics about those, and other relevant information for maintaining the format information. Below that, you have the manifests, and those manifests all point to data files or DVs or delete files. And this makes up the structure. So if you think about a tree structure, when we want to go and update that tree, we perform tree-like operations. So what do? When we want to create a new commit or a new snapshot of the table, what we do is we try and reuse as much of that old tree as possible. So you're creating new nodes and attaching data files and manifests within that update. So now you can see that we've added another manifest to the table. It's got new data files, but it's also referencing information from the previous manifests. So this is all just kind of tree-based manipulation in order to progress the state of the table. So then, if you take a look at this over time, you have this representation of a tree structure, and your next iteration of that is always going to be a mutation reusing components of the previous version of the table. And this largely makes up every mutation of Iceberg metadata. You're using this tree structure to point to the underlying data files. You're carrying statistics at the different levels. We're using different statistics at different levels of the tree. But that allows us to reuse as much as possible without having to rewrite the data. Even if you're doing delete operations or dropping data, it's always a mutation on the next version, which also allows for time travel by walking backwards through those snapshots. So at the end of the day, we have this kind of general representation of a tree structure. And this is largely what encompasses everything about Iceberg metadata at a very high level. So there are some strengths and weaknesses to this approach. It's not that this is perfect. Otherwise, we wouldn't be here talking about how we can improve. But this actually allows for very fast planning, because all you're doing is you're actually navigating this tree. You're able to prune large portions of the tree using statistics or partition information. It's stable. Every representation of the tree from the root to all the leaf nodes is captured for every state of the table. And it's very efficient in order to update that structure because you're reusing so many components of it. There are some drawbacks though. There's write latency. We actually have to produce multiple pieces of metadata in order to add just like a single file. So sometimes there's a bit of write amplification. And depending on like the small scale or how fast the data is changing, that can have an impact on the amount of metadata you're tracking and the performance of the table. And there's also issues with the levels. Like I mentioned that we're keeping different stats at different levels, and that means that we potentially have to navigate through levels to take advantage of stats. Like we can't do that at the top level. So we're not being as efficient as possible in terms of how we skip metadata. With that, we'll move on to Delta, and I'll hand it back to Ryan.
All right, so let's go through the same thing on a format I just started learning about a year ago. Now, we had looked at Delta before that, trust me. So Delta has a very different model for metadata. And again, we're talking about the content metadata here, not how to partition, not what columns are in the table or anything like that. Just how do we keep track of the actual data files, which data files are in a table. To do that, Delta has this system of deltas. And each delta is a JSON file like you see here. So v1 points to, or actually is represented by a v1.json file. And that file contains basically events like add file or remove file that encode changes to the set of files in the table. So here we're adding file A and file B, and so we just write a new Delta file with file A and file B referenced in it. Similarly, if we want to go to the next version, we simply say, okay, well now I'm adding files C through M, and I write a new Delta. Now note that these have no pointers to one another. These have no relationship. I don't have to read all prior deltas in order to create a new delta. And that's one of the really nice things about Delta is we can, with very minimal state, we can express just the changes and have a new version of the table. Of course, the drawback there is that once I get to this state where I have multiple versions, I have to go read v1, v2, v3, and so on to get the entire state of the table. And I can't just say, oh, okay, well, I see file A is in v1, and go release a task and start processing that, because I might have a delete event or a remove file event in a later version. So rather than constantly read thousands and thousands of versions, we've introduced a checkpoint. So periodically, and I think this is usually every 200 commits or so, we turn one of those commits into a checkpoint. And to do that, we take the previous checkpoint or any information about that commit, and we squash all of the changes on top of it to get a representation that we can write out and read quickly. Now, this representation, of course, we don't want to have just a single data file because these tables could be really huge. So we've divided in checkpoint v2 all of the actual file references across multiple shard files. And then we also have a checkpoint file that contains both locations of all the shards as well as any protocol or like table level information. Now we're going to put the table level information aside here for a second and just focus on those checkpoints. Notice that this is also, surprise, a tree structure that contains the entire state of the table as of some point in time. And that's going to be important. So now, like Iceberg, there are some trade-offs. There are good things about this and bad things. So first of all, we get fast commits where you don't have quite so much state to keep around. Iceberg commits are actually fairly complicated because you're making a change, and it's not like you're making a change and making sure that you can still do that. You may have altered physical files. You may have you may need to rewrite multiple metadata files. So they can be generally more expensive. So with Delta, you avoid those problems. It's also a lot easier to detect changes because the only things that have changed are in those Delta files. And then these are also using Parquet for the shards of those checkpoints. So you get essentially columnar scan planning, which is a really good thing. Still, there are some weaknesses as well. So that log replay, so getting all of the events since the checkpoint, and then smushing them into the current table state is actually a fairly expensive process because you're reading up to 200 small files. There are analogs of that problem on the Iceberg side too, but you have to do that. There's no metadata filtering operation that allows you to skip any one of those deltas against the last checkpoint. Checkpoints are also fairly substantial. So you're rewriting the entire table state every 200 commits as a checkpoint. And so we would like to make that process a lot more lightweight. And also, like, if you have a really, really huge commit, this is kind of minor, you have to write the whole thing as a JSON file. So if you're writing a million new data files into a table, that can be quite slow because you have to put them in a single delta file. So we've sort of set the stage with both the background on Iceberg and the background on Delta. Well, what do we do to bring these two different worlds together? And the idea here is pretty easy. We've hit it in the slides already. It's Iceberg as checkpoints. So let's go into what that might look like. Well, here is Iceberg metadata, and here is a Delta checkpoint. And as you can see, we can kind of just change the labels. So that's our plan. We're going to rename a bunch of classes in Java, just see what happens. No, it's actually not this simple. But let's take a minute and think through. If we were to do this, what would we gain and where would we go? So if we just said, okay, the unified table format is going to be Delta with current Iceberg metadata underneath as checkpoints, we would actually get some really cool properties out of this. So first of all, we would get incremental checkpoint updates. Iceberg is really good at reusing work and making changes to the tree structure that we use because we don't have deltas. So, we try to make the updates to our version tree as efficient as possible. And we've gotten pretty good at that over the years. So, where we don't have incremental, like cheaper checkpoints on the Delta side, we can get that for free by integrating Iceberg metadata. Iceberg also, because we have a different way of cleaning things up, we get to omit deletes from checkpoints, or omit deletes when we rewrite any data file. So rather than carrying these delete file entries around for 7 days, and then using that as a signal that we can delete data files, if we go with the Iceberg model, then we can actually make the entire checkpoint metadata tree more efficient by storing less. So essentially, every checkpoint, get rid of what churned out and just have the data that is still in the table. And that actually can be very, very impactful if you have high churn in your tables. In addition, the metadata inherits Iceberg's property of being fairly cache friendly because we're reusing the metadata files across checkpoints. And cache friendly is a really good thing if you want fast query planning and things like that. But then it's not all free stuff in this world. So if this were our plan for unification moving forward, there are some substantial problems. So first of all, from an Iceberg perspective, we would be saying, okay, well, Iceberg versions, then we have this other kind of way to encode changes to the table. And that's a new concept of adding deltas to Iceberg and then brings in the latency of log replay. So it would make the Iceberg read path significantly slower to do it this way. So that's not a great outcome. And also, honestly, probably not something that the Iceberg community would agree to. Like, hey, we want to unify the formats, but we're going to make reads slower and we're going to increase the complexity. So we need to figure out a way to work around that. Also, Iceberg metadata is not like Delta's checkpoint metadata in that it's not yet columnar. So we actually have to work around some of the deficiencies of Iceberg in this world. So like maybe we should do something about that. And then we have other problems like file locations in Iceberg are absolute. In Delta, they're relative, so that you can pick up all the files in the table, move them somewhere, and the table just works. So we can't really do this because writing out checkpoints in this world would mean you can no longer move your table around, which I've heard people are doing for disaster recovery, but it's S3, who needs it? All right, so what we need to do is, I think, expand on this idea of Iceberg checkpoints. Use the things that look alike, but solve some of these deficiencies. So how do we do that? Well, this is the heart of the plan that we have. Number one, we need to make some Iceberg changes so that we can have relative paths, columnar metadata, and sort of, get Iceberg metadata to the point where delta checkpoints are so that we're not regressing. Again, we want to be improving both formats at the same time with unification so that people have a reason to do this. So we will do that. We will also introduce one file commits. And this is our plan for really making metadata supercharged and basically better than Delta is, better than Iceberg is at the same time. Now we need that in Delta because Iceberg commits are slower, right? We can't have a checkpoint and keep them updated and actually get rid of the deltas unless we're producing a checkpoint on every commit operation in Delta. In order to do that, we have to have something that is about the same efficiency and cost for quick writes to that table. So Delta having single file writes, that's a really big step. So we want to introduce single file writes on the Iceberg side as well. Now, that is roughly what we want to do. So take this idea of checkpoints with Iceberg metadata. Improve Iceberg metadata to the point where we can produce a checkpoint really quickly and incrementally like we do in Iceberg. So make it even faster to keep these up to date. And then improve Delta by having a checkpoint for every single commit. Get rid of log replay and essentially remove the requirement for distributed planning and have faster metadata operations overall. It's also going to basically make cacheability a whole lot better because we're going to have longer term persistent metadata files rather than rewriting them all the time. So that's the idea. How do we get there? Well, here is the basics. So we're going to start and say, okay, we want to, like Iceberg, maintain the metadata tree, the content metadata, every single commit. Okay. Now, we also want single file commits. So let's take advantage of the fact that we can write more in a commit than we necessarily need to, given the latency to and from S3. So rather than just writing the files that changed in the data file that we write for every commit, we're going to just keep copying stuff. So as I write a single manifest, my next commit rewrites the entire thing rather than referring to the last manifest. And that gets us this single file commit. This is great. But again, as we talked about in Iceberg metadata, we know that we're going to need a tree structure because we can't just carry everything forward every commit. So what we want to do is actually make the tree adaptive. So for when the root file fills up, when it gets too large to be a very quick commit operation, and you start having latency due to the throughput and size of that file, rather than just the round trip to S3, then we cut another manifest file. So you should get this sort of sawtooth behavior where your commit latency slightly creeps up, and then we cut another manifest file, and it drops back down. So that is our rough plan for how to introduce single file commits. Of course, we're also going to make other substantial changes here. Basically, everything that we need to change here in Iceberg v4, the Iceberg side of this, is allow data and delete files in the root manifest. Make it super fast for those single file commits to happen. We're also going to, another idea that we think is important is using DVs at the metadata level so that we don't have to rewrite manifests all the time. So rather than rewriting one of the leaf manifests and committing a new root manifest, we can just encode a DV against one of the existing manifests. Again, increasing our ability to cache metadata, have faster scan planning, and also this removes the large number of files that both formats accumulate. Every single commit in Iceberg creates a manifest, and those stack up and accumulate until you eventually compact them. Every commit in Delta creates a new Delta, and you have to read all of those. But if you're continually rewriting that root level, then you keep things nice and compact, and again, really speed up that commit path as well as the read path. So that is, and I'm almost perfectly at time. That is the plan. I wish we had time for questions, but I think we're getting kicked out. Thank you, everyone.
Thank you.